Okay, so good day everybody. So, we are talking about subgroup and some of the properties of the subgroups. We will discuss some more properties of the subgroups. Especially, we will take two subgroups, then we will see whether their union is a subgroup, intersection is a subgroup, their product. We will define how, what do you mean by a product of a subgroup, two sets. So, these are the properties we will discuss now. So, for that, so let us take a group. Let G be a group under this operation star group, and H and K be two subgroups of G, non-empty subgroup, be two non-empty subgroup of G. Okay. Then we will discuss some of the properties. We want to know whether their intersection is again a subgroup or not, their union is a subgroup, their product, these two sets. So, G is a set which is a group under this operator, and we have a two subset H and K, where H and K are both subgroup under this induce operator of this. So, H is also a group and K is also a group, capital K is a set. Okay. Now, the first theorem is when their intersection is also a group, H intersection K is a subgroup. Okay. So, this we have to prove, this we have to show first. Okay. How to prove this? So, first of all we need to show this intersection is non-empty. So, suppose W is the intersection, this means this region. So, W is the intersection. So, why this is non-empty? Because the identity element of the group E, now this H and K are both subgroup. So, E must belongs to H and E must belongs to K, the identity element of the group. Then this implies E must belongs to their intersection. So, this implies this is non-empty subset of G, this W. So, W is non-empty. Now, we need to show that W is a subgroup of G. So, for that we will use one of the necessary and sufficient condition to show W is a subgroup of G. So, for that what we take, so this is our W, this. So, we take two element from W. So, W is basically, and then we need to show for all A B from W, we need to show that A star B inverse is in W. Then we are done. Then we remember this is one of the necessary and sufficient condition to be a set, subset is a group. So, we want to show this is not yet done. Okay. Now, this implies A B belongs to H and A B belongs to K, both, because they both belongs to their intersection. So, they both belongs to this. Now, this is a group, this is a group. So, this implies and A star B inverse belongs to a K, because this is a group. So, we know this property, this is a necessary condition of a group, because B is an element. So, B inverse also exists in a group. So, now A is an element, B inverse is an element. So, closure property A star B inverse must be this. So, now this implies A star B inverse belongs to W. So, hence this implies that under this there is a sufficient, this is a sufficient condition, and this is true for all A B. So, this implies this is a subgroup of G. Subgroup of G. Okay. So, the intersection is a subgroup. Now, we want to know the union, whether if we have two subgroup H and K, whether their union is also a subgroup. So, we will see union is it need not be a subgroup. So, the question is the union also a subgroup? So, answer is no, not always. Not always. Okay. Then we have to have a counter example for where it is not happening to be a subgroup, where H and K both are subgroup, but their union is not a subgroup. Okay. So, what is the example? So, if you take a group G to be the Z class. Okay. So, this is the set, we consider this along with this operation is G is a group. This is the set of all integer. Okay. Now, if we consider two subgroup 2Z plus and 3Z plus, these two are the subgroup of G. Now, the union is basically all the elements which are either multiple of 2 or multiple of 3, all the integer which are multiple of 2, multiple of 3. Now, the union is not a subgroup. Why? Because 2 belongs to H and 3 belongs to K. Now, this implies 2 and 3 both belongs to H union K, but what is 2 plus 3? So, if it is a group, then the closure property must satisfy, but 2 plus 3 is 5. So, 5 is neither belongs to H nor belongs to K. So, 5 does not belongs to H union K. So, this implies closure property is failure. So, that means this is not a subgroup. So, this is an example where H union K is plus, under this plus is not a subgroup. So, the intersection we know is a subgroup, we just prove it, but union need not be a subgroup. Okay, now we define the product of two subset, and we are interested to see whether this is again a subgroup. So, again G is a group and we have to G is a group under this binary or composition. We have two subset H and K, okay, and suppose they are both subgroup, are both subgroup of G, non-empty subgroup. So, subgroup. So, every group, if G is a group, then G must be non-empty. So, okay. So, now because at least identity element will be there. So, the singleton group is the ID one, I mean identity element form a singleton group, that is also a group. So, every group must be non-empty. In the definition of the group we discussed that. Okay, now we want to define a set. This is called product set. This is nothing but H star K, or simplicity we can just write, we can omit star, we can just write H K, small k, this is small k. So, this means H operate with K under this operation. If it is multiplicative sense, this is okay. Otherwise, if it is additive sense, then this will be written as H plus K and this will be H plus K, small k. But anyway, this is just a operator notation. So, now H is coming from H and K is coming from K. Okay. Now, this is the way how we define this product of two set. This is not a Cartesian product. Cartesian product is the ordered pair, but this is an element in the group itself in G. Okay, now we want to see whether this is a question is whether this is a set W, whether this W is a subgroup or not. subgroup or not, because this H and K is again a subset of G, and it is a non-empty subset. Why? Because E must belongs to this, because E belongs to H K always. So, H K, this is non-empty subset. Now, the question is whether this is a subgroup or not. Okay. So, again it is need not be a subgroup always. So, you have to take an example where it is not a subgroup. So, we take the example of polynomial group, that S 3. So, we consider set of all polynomial of degree 3. So, this is our S 1 2 3, and if we consider set of all polynomial of degree 3, this will be denoted by, say this is identity polynomial, this will be denoted by P 0, and then P 1 is basically 1 2 3 2 3 1, this is P 1, this is nothing but 1 is going to 2, 2 is going to 3, 3 is going to 1. This is a even permutation, this is a cycle. So, P 2 is nothing but 1 2 3 3 2 3 1 2 3 1 2, that means 1 is going to 3, 3 is going to 2, again 2 is going to 1. So, P 3 1 2 3, then again 1 3 2 is basically 2 2 3, this is a even permutation. Then P 4 and P 5 1 2 3, P 4 is 3 2 1, 3 2 1 is basically 1 is going to 3, 3 is going to 2, and P 5 we have P 5 1 2 3, and we have 2 1 3. So, this is 1 2, these three are even permutation, and we have identity permutation. Okay. Now, this is our set. Now, we know this is a group, this is called symmetric group. Under this composition, because permutation is a bijective mapping. So, if you take two bijective mapping, if we compose, this will again give us a bijective mapping. So, in the permutation sense, it is the product of two permutation is again a permutation. Okay. So, product of cycle basically. So, now this is a group, this is our G, this is a group. Now, we want to take two subgroup of this H and K. So, you can just okay, you can just erase this part. Now we know the P 0 to P 5. Now, if you take H to be say P 0 and P 3 and K to be P 0 and say P 4. Now, we can verify that these two are the subgroup of G under this operation. So, we can easily verify that this both of these are subgroup of G. Now, what is their product? Product is basically H K. So, all the possibilities of this. So, this will give us P 0, P 1, P 3, P 4. Okay. Now, this is not a subgroup, we can verify that. This is not a subgroup, not a subgroup of G. Okay. This is not a subgroup of G, because P 1 is not having inverse in this group, and even we can verify the composition may not be satisfying. So, this is an example where product is not a subgroup. Now, so we want to know that is there any is there any sufficient condition which can say that this will be subgroup if this condition is satisfied. So, that we want to explore. So, we want to know a necessary and sufficient condition under which this product of two subset is again a group. So, this will state by a theorem. So, this is a theorem. Okay, so this is telling let H and K be two subgroups of a group G. So, we can define the operator also. Then H into K is a subgroup of G if and only if G if and only if H k is equal to K h, if they are commutative in the sense, if H k is equal to K h. Okay. So, there is two part, if part and converse part. So, necessary part and sufficient part. So, we just going to try to prove this. Okay, first of all we assume this is a subgroup. Suppose H and K is a subgroup of G. Then we want to show these two set are same. So, for that what we need to show? We need to take an element from this set and we need to show that this is an element in H and K. So, if you take an element from this set, then this implies, so this is a group, this implies inverse exists, inverse is also a group. Okay, now, if we take now inverse exists because this is a group. So, now we can take this to be x inverse to be, this is belongs to H k. So, H 1 and some k 1. So, now this gives us x to be, if we take the inverse of this, k inverse, k 1 inverse, H 1 inverse. So, this is a member of K h. So, if you take an element from here, we can see this is an element of here. So, reversely also we can do that. We can take a y from here with the same trick, we can show this is an element of here. So, this is a subset of this is a subset of this. So, these two set are same. Now, conversely you want to see this condition, this is a necessary and sufficient condition. So, you want to see if we have this condition, then we want to know whether this is this H and K is a subgroup or not. So, that part we have to convince. Okay, so, to do so, we just take conversely, this is the other part of the proof. Suppose these two sets are same. Suppose these two sets are same. Okay. Now, we want to see whether H k is a group or not. So, for that we will use one of the necessary and sufficient conditions. So, we take, let us take two elements from this and then we are going to show that two properties are there, na? S star q is also belongs to this, and if you take an element q inverse belongs to this. So, if you can prove these two, then we are done. So, we will try to prove the first one and second one I will leave you for the exercise. Okay. So, now if p q is this, so p will be something like h 2 k 2 and q will be, we have taken k 1 k 2, anyway you can take k 3 k 4 and q will be k 4 h 4, something like that. So, if you take the product p q, so it is basically h 3 k 3 h 4 k 4. Now, this is basically we can combine this h 3 k 3 k, this is by the associativity rule of the operation star. These are basically star operation. Okay. Now, this is an element from k h. Now, k h is same as this. So, there exists another element from this which is same. need not be this is commutative, we are not claiming that, but there has to be some element like K 3. So, there has to be some H 5 K 5 which will be in this, okay, because these two sets are same. So, now this will give us H 3 K 5 and K 5 H 4. So, this is another H, this is another K. So, this belongs to H K, this belongs to H K. Okay. This is the first part, and the second part we have to show that Q inverse is also belongs to H Q. So, this you can easily by this taking this type of term you can easily verify that. Okay. So, this is the necessary and sufficient condition to be a to be a subgroup under G. So, now we will define coset of a subgroup. Okay. So, first we define the left coset. So, for that let us take G be a group, and H be a subgroup of G, Okay. So, then we define, then let A be an element in G, any element in G. So, this is our set G, this is H which is a subgroup. Now, we take an element from G, this may be from here, this may be from here, does not matter. So, we take an element from G anywhere, it could be in H also. Now, we define this left coset. So, H A H, this is basically all the sets, all the elements like H, H is coming from H. Okay. H is coming from H. So, this is in multiplicative sense, if star is multiplicative sense. Now, if star is additive sense, this will be A plus H. If star is the additive sense. Okay. But anyway, this is the operation. So, we will just take this notation and we assume the star is in multiplicative sense. Anyway, this is just a binary operator, it could be addition, it could be anything. So, now, so this is the definition of the left coset. This is the definition of the left coset. Okay. For example, if we take say Z, so if you take the group to be set of integer. Okay. Now, if you take a subgroup of G, now what are the left coset? So, left coset will be of the form, say we take an element A from G, 0 is an element. So, 0 plus H, this is a left coset, this is same as H. Now, 1 plus H, which is basically all the elements of the form 3 n plus 1, n is coming from Z like this, 2 plus H, 3 n plus 2 like this. Okay. So, this is in additive sense. So, that is why it is in this form, otherwise if it is multiplicative sense it is 2 H 1 H like this. So, this is one example of this. Now, we will know some properties of this coset. Okay. So, now, this is a group G under this operator and this is our H. Now, the first property is telling us if we take the element A from H itself. Okay. So, then it is telling us H is basically same as H. Okay, if the L, because this is H is a, we have to prove this, H is a subgroup. H is a subgroup. So, if we take the element from H itself, then it will give us a same set H. So, how to show that? To show that, this is basically we need to show this is a subset of this. Now, H, this is also, this is a subset of this. This is this is no doubt, because H we defined as, this is the H some H 1, where H 1 is coming from H, and H is a subgroup. So, this is also belongs to H. So, this is a subset of this. Now, only thing we need to show, if you take an element from H, say we take an element from H, say some H star, any element, for all element, we need to show that there exists some H 1 such that H 1 H star, sorry, H star equal to H 1. Okay. So, now how to show this? Now, if you take an element from here H, this is basically H star. Now, that means H star such H 1 exists. So, H 1 will exist, because this is basically H 1 is basically product of this. So, how to show this? So, let us take an element from here. So, this is basically our H star. Now, we want to show there exists an element here H 1 such that H compose with H 1. So, H compose with H 1 will give us H star. So, that means H 1 is nothing but H star H inverse, and that inverse exists here, because H is a element here. So, this is the existence of such H 1. So, that means this is the subset of this also. So, if you take the element from H, then this coset is same as H. Now, if you take an element outside this, then what is happening, that we will see in the next class. Thank you.